I'm Eric Mazur. I'm a professor of physics at Harvard University and also Dean of Applied Physics. So my group has for many years looked at the interaction of ultrashort laser pulses with matter, typically shorter than picoseconds, so femtosecond laser pulses and semiconductors and transparent materials. We were one of the very first groups to have a femtosecond laser. I sent some of my graduate students to Bell Labs in the 1990s to learn about, no, actually late 80s, to learn about colliding pulse mode lock lasers. And ever since then, we've done both time-resolved measurements as well as looking at the interaction of really high-intensity pulses with matter. So femtosecond pulses have two advantages. One is they're very short, so you can time-resolve all but the absolute fastest processes in materials. But the other one is that by essentially squeezing the light into a very short time interval, the intensity becomes very high. And because the intensity is so high, you can actually use light to manipulate matter. Normally, it's matter that determines what happens to the light. But at these high intensities, the roles are reversed. It's light that determines what happens to matter. So you can modify the structure of matter. You can turn a semiconductor into a metal, either permanently or temporarily. You can dope materials with other elements to a degree that is not possible with other techniques. Or in transparent matter, which is something that my group pioneered sort of in the late 90s, you can actually micromachine, change the structure of transparent material in the bulk of the material, not at the surface, but inside the bulk. More recently, we started to become more active in nanophotonics, the manipulation of light at the nanoscale. And in fact, this past year, my group managed to manufacture a material that has zero index of refraction, which means no refraction, which also means an infinite wavelength and an infinite phase speed. So in other words, the electromagnetic field is uniform throughout this material, much in the same way that the electric field is uniform in a conductor. In a sense, the photons inside this material behave almost like electrons in a conductor. This gives you the ability to manipulate light at the nanoscale in ways that were not possible before. In addition to my work in optics, I've been very concerned about our approaches to teaching. Typically, professors, and physicists maybe in particular, do not apply the scholarship that they apply to their research in teaching, right? For research, for example, we come to meetings, like the SPIE meetings, in order to exchange ideas, to learn from each other, to disseminate knowledge, to learn about best practices in research. But in teaching, nothing like that happens. We get assigned a course, we go into the classroom, we do what our professors did to us, who incidentally probably did what was done to them by their professors all the way back to the Middle Ages, long before Gutenberg invented the printing press. And if you step into a typical classroom, what do you see? You see an instructor in front of a class, or in front of an auditorium, which was developed incidentally by the Greeks to make performances, not to educate, delivering information, because that's what most of the lectures are. They're simply delivering information. Well, that's not the key to education. The key to education is for the learner to make sense of that information. So I discovered that my quote-unquote brilliant lectures, even though they were highly appreciated by my pre-medical students, did not accomplish what I really wanted them to accomplish. They did not learn even the most basic principles. And that was because I was focusing on this information transfer. The hard part is for the learner to make sense of that information, this aha moment. So I decided, why am I actually reading the book to them? They should be reading the book, so that in the classroom, I can help them make sense of the information. So that's when I started to teach by questioning. That led to peer instruction, where I ask a question, the students commit to an answer, then they talk to their neighbor, trying to convince their neighbor, have these aha moments, oh yes, that normally they wouldn't have in the class. That then led to the development of the clicker and the flipped classroom, which, much to my surprise and beyond my wildest imagination, took off around the globe and in many different disciplines and in many different educational levels, from post-secondary education, where I am, to secondary and even elementary education. No, I think a lot of research is completely, a lot of the big results are completely serendipitous. I mean, they tend to happen in unexplored areas, and even though there might be many failures on the road. Look at some of the biggest inventions, right? Thomas Edison, the light bulb. He didn't just invent a light bulb. He had this crazy idea that he was going to make a light bulb, and I think he made something like 300 prototypes that failed, one after the other. Everybody said, stop it, go do something useful, but he persisted. Look at the Nobel Prize in 2010, Andre Geim, graphene. Everybody talks about graphene. I heard the word several times at this meeting here today. He did that with Scotch tape. I mean, nobody had heard of Andre Geim before he did that. It was literally nanotechnology on a nano budget, unplanned, sort of trying something new and then discovering something that nobody else had ever thought of. And I think a lot of innovation, a lot of advances in science are much more serendipitous than many people like to admit.